Now, functions that have the form f of x equal x to the n have derivatives that follow a particular pattern. From the previous chapter, you may have noticed that if f of x was equal to x, then the derivative of f with respect to x was 1. If f of x was x squared, then the derivative of f was 2x. Now what we're going to do is we're going to use our definition. We're going to continue this pattern and see if we can recognize the pattern so we can just write out a rule for doing power functions, which we'll call the power rule. If f of x equals x cubed, then let's use that definition of a derivative and see what we end up with. The definition of a derivative is the limit as h goes to 0 of f of x plus h minus f of x, all divided by h. So what I'm going to have to do is figure out what f of x plus h is, put f of x in here, and do lots of algebra. If f of x is x cubed, f of x plus h means we put in place of x plus h, so we get the quantity x plus h cubed. F of x is just x cubed, so we put those things in here. And we can't possibly do this limit now because if h approaches 0, we're going to get 0 over 0 out of this fraction. So what I need to do is I need to expand x plus h cubed, and in the process, see what I can get to simplify here. So if I do x plus h times x plus h times x plus h, that's what x plus h cubed means. When I go ahead and FOIL these first two out, I get x squared plus 2hx plus h squared, and then I have to multiply that by x plus h. If I go ahead and distribute the x on each of those three terms and the h on each one of those three terms, I get x cubed plus 2hx squared plus x h squared plus hx squared plus 2h squared x plus h cubed. If I go ahead and combine my like terms, you'll notice that I have a 2hx squared and an hx squared. That's what gives me the 3xh squared. And I also have a similar set of terms that give me the 3x squared h. Combining all those terms together gives me the four pieces that you see right here. And now I notice that the x cubes can go ahead and cancel. What I end up getting is 3x squared h plus 3x h squared plus h cubed, all divided by h, and I still need to take the limit as h approaches 0. But to be able to do that limit, I'm going to go ahead and factor out an h from each of the terms on top. And when I cancel that with the one on the bottom, I end up with 3x squared plus 3xh plus h squared. The limit of that as h approaches 0. As h approaches 0, the second term is going to disappear because it has an h in it, and so is the third term. But since the first term doesn't have an h in it, nothing happens to that. What we end up with is 3x squared. I could do this for even higher powers. I could do this for x to the 4th, x to the 5th, and x to the 6th. But each time I'll have to do x plus h to the corresponding power, and that's going to get kind of ugly to do algebraically. But if I do it for x to the 4th, I end up getting 4x cubed. For x cubed, like we just saw, the derivative was 3x squared. Take a look at the pattern here. We start out with 1, 2x, 3x squared, 4x cubed. 1, 2, 3, 4. But notice that the powers over here were 1, 2, 3, 4. So when we take the derivative, the power must come down in front. X squared becomes a 2 in front. The cube becomes the 3 in front. and the 4 becomes the 4 in front. Furthermore, what you'll notice is if the power was a 2 in the derivative, it was a 1. If the power was a 3 in the derivative, it was a 2, 1 less. And if the power was 4 in the derivative, it was a 3, again, 1 less. Now, you might be worried about this first one, but what is a power 1 less than x to the first? Well, it's x to the 0. And remember, anything to the 0th power is 1. So it also fits the pattern. If f of x is equal to x to the n for any real number n, then the derivative has this pattern, and what the derivative is n x to the n minus 1. Notice we've taken 1 away from the power, and the power that appeared in the original function in the derivative, it becomes in front. The derivative of f of x equals x to the n is found by multiplying by the exponent n, decreasing the exponent by 1. If I have f of x equal x to the 5th, then the derivative of that, well, we bring the power down, so it becomes 5, and then we take 1 away from the power, we get x to the 4th. So the derivative with respect to x of x to the 5th is 5x to the 4th. If we have g of t equals t to the 100, I've changed the variable here, but we still use the same process, and we want to find the derivative of g with respect to t. Well, when we take the derivative with respect to t, we're going to bring the power down, so we get a 100 out in front. Take 1 away from the power, we get t to the 99th. It would really be ugly if we were to do this by the definition, because to figure out the derivative, we'd have to end up taking t plus h to the 100th power, and we'd have to expand that out. And that would take us a little bit of time. So this rule, the power rule here, is going to save us a lot of work.